Okay, so here's a problem that we've talked about a little bit before. We're going to write equations for shear force and bending moment. And in this particular case, because of the loading and the supports with the overhang, we're going to need a set of equations that are going to vary from 0 to 4, and then from 4 to, I guess that would be 20. So before we get started, let's just imagine a cut somewhere there between 0 and 4. Would you want to work the left side or the right side? I think the left's an easy one there. So I wouldn't need any of my reactions. I could go ahead and start that right now. Then the second one, let's say I make a cut here. And now I'm looking at the left side or the right side. Which one looks easier to you? About the same, but I think the right might be a little cleaner to put together. Either way would work. If you did the left side, this would be a function of x. If you do this side, it's still going to be a function of x. You're not going to save anything there. So with that overall strategy, it looks like the only reaction I really need is C. So with that as my starting point, I'll look at CY and CX, and I'll say here's BY. Now I'm going to reduce my distributed load to a concentrated equivalent. This is going to get a little messy. I'm sorry about this. So there's the distributed load. What's the value of that load? It's going to be base times height, which is 16 times 2. Yeah, 32. Now I'm going to want CY, so I'm going to sum my moments about B. So I'm going to want this distance. What's that distance from B to the centroid? Should be 8 feet, right? Half the distance. So now when I sum moments about B, make sure my free body is in equilibrium, I should be able to find CY. So about B, I'll start over with this 8 kip force. What kind of moment about B does that create? Positive or negative? Positive. So I've got 8 kips, and the moment arm is 4 feet. And then about B, I've got this concentrated equivalent, which creates positive or negative moment? Negative. And that's 32 kips times 8 feet. And then CY, again, the moment about B, CY, that creates positive. And that has a moment arm of 16. So what is CY equal to? Somebody got to help me out. It's something less than 16. That's all I can say. 14? Is that what you got? Anybody else get 14? Yep. Cool. So now I can go and cut my free bodies and find my equation. So I'll do the first one between 0 and 4. So that's this little piece here. So I just have the 8 kip force, and I'm cutting it at a distance x, and then we'll look at our interior forces, which would be positive shear and positive bending moment. So not a lot to take care of here. So when we sum moments, again using right-hand rule for my positive moments, and at the cut we're going to make sure it's 0. So our interior moment is what? Positive or negative? Positive. And then the 8 kip moment about the cut is also positive. But it has a moment arm of x. And that's it. So it looks like the moment is just equal to minus 8x. And that would be kip phi. And then we're going to sum forces in the y direction. And looking at our free body diagram, our shear force is down, our applied load 8 kips is down, so it looks like the shear is equal to minus 8 kips. It's constant. I think you can do a quick check there and see that the derivative of the moment is equal to the shear, so that seems comforting. That was a pretty easy one. Now in the second case, between 4 and 20, at the beginning of the problem we talked about working the right hand side, so I'm going to draw my free body for that. I have my reaction at CY, which we found was 14. We know that this is coming at a distance x. So what is the remaining length of my segment here? Yeah, 20 minus x. Now the load that is applied is uniformly distributed. It has an intensity of 2 kips per foot. We're going to turn that into a concentrated equivalent force, F, and from the cut, acting through some distance D, right? Yeah.
Why would, instead of 20 minus x, why wouldn't it be 16?
Remember, we're measuring x all the way from the left.
Oh.
So we've got to include that 4. So the distance from here to the cut would be x, and then the total distance is 20. Does that make sense?
Yeah.
So what would be our force? It's a rectangle, so base times height, so that would be 2 times 20 minus x, right? And then what's our distance? Well, half the base is x, is 20 minus x, so half of that. And then internally, I have my positive shear force and my positive bending moment. So I think that's a complete free body diagram, and now we can just apply our statics to it. And if we take our time, we should be okay. So let's see. We'll sum moments about the cut again. Using right-hand rules, my sign convention, make sure we're in equilibrium. So starting here with the moment, what kind of moment is this? Positive or negative? Negative. F creates what kind of moment about the cut? Positive or negative? Negative. So we got minus F. Remember F is 2 times 20 minus x. And then times this moment arm D, which is 20 minus x over 2. And what else do I have? I've got this reaction force 14, and about the cut, what is it? What kind of moment does it create? Positive. So I've got 14 times its moment arm, which is 20 minus x. So we want to solve for m. So when I do that, let's see. The 2's cancel, and I just get 20 minus x squared, and there's a negative sign in front of that. And then this piece over here. Obviously, you could factor that out if you want, but really, in the heat of the exam, it's still an equation and it's still valid. Just leave it alone, unless you're one of those people who just must do it. I am not one of those people. That works for me. What's the moment at C? What's the value of the moment at C? It is a pin. What's the moment of the pin? 0. So does our equation say the moment is 0 at x equals 20? Yes, it does. I like that. So that gives me some hope. Then we're going to sum forces in the y direction. Looking at that, we've got the shear force acting up. We've got our equivalent force acting down, so that's minus 2 times 20 minus x. And then we've got 14 acting up. So I'm going to solve for the shear. Let's see, what do we get? We get 2 times 20 minus x plus, that would not be plus, minus 14? That I could probably factor out some if I wanted to. If you take the derivative of this, forget the sign, you take the derivative of this, what do you get? You get 2 times x minus 20, and then the sign, and then the negative comes out, cancels that, so that's right. And you take the derivative of this, you get negative 14. So that seems to match. So it looks like the derivative of the moment is equal to the shear again. Now let's see these things match. So this is going to be a tough one to match the shear. Why? Because as you come from the left side and you get right there, you're going to get a value of shear. And then this reaction is going to affect that. And then when you go just to the right, you'll get a different value. So if you try to match these two shear values at x equal 4, you're going to be off by exactly by. But you can match the moments. If you put 4 in here, you get what? Negative 32. If you put 4 in there, I don't know what you get. Somebody put that in there. Hopefully you'll get negative 32. That will just give you a chance to make sure things are working. Anybody get negative 32? Yep, good. So just to check this one, we got negative 8 on this side, and then by acting up. By is going to be 18 up. So that means I'm going to go from negative 8 plus 18 would give me positive 10. And at x equal 4...
It's 26.
Sorry?
By is 26.
26. Oh, sorry, 26, yeah. So that would be 18. What's this at x equal 4? 16, 32, 32 minus... That's right, isn't it? I think that's right. So any questions about that? Again, this could be a lot easier. You could factor this out pretty quickly and get an easier answer to deal with. But you don't have to, so don't feel the need to do that unless you just must. Okay.